Hello, in this video we are going to look at the velocity gradient, how it's written, and also at a very useful decomposition in the context of fluid dynamics. So the velocity gradient can be written in component form as follows. So I'm going to use the usual convention in fluid dynamics, u for the velocity in the x direction, y, v in the velocity for the velocity in the y direction, and w for the velocity in the z direction. So I'm going to write du by dx. I'm going to have du by dy here, and then du by dz. Then on the second line I have dv by dx, dv by dy, and then dv by dz. And on the third line I'm going to have dw by dx, dw by dy, and dw by dz. And I can also write down each individual components of this gradient of velocity tensor by writing it in a more condensed form and saying that the component ij will be dui over dxj. Here essentially introducing the convention that I refers to the line, okay, to the row, and j refers to the column, okay. U1 being U, U2 being V, and U3 being W, and in a similar fashion, X1 being X, X2 being Y, and X3 being Z. So there's a very useful decomposition of this tensor, which is a type of decomposition we use a lot in linear algebra, and it is to actually decompose this vector into its symmetric and its tensor into symmetric and anti-symmetric parts. So what I can write is that dui over dxj, so that's my velocity gradient tensor, will be equal to eij, that's one tensor, plus omega ij. And this will be the symmetric part, and this will be the anti-symmetric part. Okay, and the idea behind this is that you will see that in a second, is that it helps understand what is happening in our flow due to the velocity. So, due to the velocity gradient. So this will be called the strain rate tensor, and this one will be called the vorticity tensor. And their definition is as follows. So Eij, as it is the symmetric part of the velocity gradient tensor, is going to be 1/2 of dui over dxj, and to make it symmetric I have to swap the opponent and the components and add that, so that's going to be duj over dxi. And then you can obviously, because it's a symmetric tensor, and because we have swapped the indices in this fashion, you can easily check that it is symmetric by verifying that eij equals eji. Okay, and the definition of the antisymmetric tensor, or the vorticity tensor, is omega ij is 1/2 of dui over dxj minus duj over dxi. Okay, and in a similar fashion you can verify here that omega ij is anti-symmetric, that is to say that omega ij equals minus omega ji. These are very easy to check, and similarly that we can check that there omega ij equals 0 for I equals j. This is a property of the antisymmetric tensor, is that not only its trace is 0, but all the components on its diagonal are 0. Okay? And there's a slight remark here that as a consequence of this, there is a remark, is that if you have an incompressible flow, in other words, if the divergence of the velocity is 0, or let's just have a look at what the divergence of the velocity is. So that's going to be the trace of the velocity gradient tensor, so dui over dxi. And in other words, this is EII plus omega II. But in fact, because omega ij is 0 for I equals j, this term is always going to be 0. All the components of the summation are 0. And so in other words, what we have is that the contribution from the vorticity tensor to the divergence of the velocity is 0, and therefore the divergence of the velocity is entirely contained within the trace of the strain rate tensor. Okay, so now let's have a look at what these tensors do in practice. So let's first have a look at the strain rate tensor. So the strain rate tensor, it is responsible for extension and contractions within the flow. And so if we want to convince ourselves of this, we can take an example. And for the sake of this example, I'm just going to take my strain rate tensor in 2 dimensions. So I'm going to take 1, 0, 0, and I'm going to take -1 here to make sure that my flow is incompressible. That is to say that the trace of this tensor is 0. And so from this, I can just, based on the definition of my strain rate tensor, I can read out that the component of the velocity gradient come out very easily. So du by dx equals 1. This is this element of the diagonal. And similarly, I get that dv by dy equals -1 coming from this element here of the diagonal. And note that if I write this in this fashion, then I'm assuming effectively that the vorticity tensor is 0 everywhere. And so if I solve this and I take, for instance, the solution that u equals x and that v equals -y, I'm dropping the constants of integration because here I'm just taking an example. Then I obtain the following flow, exemplified here, for which if I want to draw what the flow is doing in my domain, in the xy domain, then u goes, u has the sign of x, so there will be velocity in this direction, here and there. In this, here there will be velocity in the other direction, in these quadrants. And v goes like -y, so there will be downward velocity here and upward velocity in the bottom half of the domain, which essentially indicates that we're going to have velocity in this direction in this quadrant, velocity in this direction in this quadrant, in this direction here, and in this direction here. In other words, we have created a flow whose streamlines are going to be looking like the ones that I'm drawing right now. Okay? And so what we have done here is essentially a flow for which there is a contraction along the y-axis and an extension, or we're pulling the fluid away in extension along the x-axis. Okay, so this is what this strain rate tensor is doing. So again, there's contraction when there is a -1 here, and extension when there is a +1 here. Okay, so this is one example, but for the sake of really apprehending this tensor a bit better, we can take another example for which, for instance, now I'm going to specify the gradient of velocity tensor, and I'm going to say that the gradient of velocity tensor, I'm not going to focus on the diagonal, we just saw what the diagonal was doing, so I'm just going to put zeros along the diagonal. And then I want no contribution in the vorticity tensor, so I need to make sure that the value that I put here is the same as here. So I have a symmetric tensor, and that symmetric tensor that I'm picking is by just putting 1s in there. So when I do this, essentially, if I read out these terms based on the definition of the velocity gradient, I get that du by dy is 1 and dv by dx is 1, and the other derivatives are 0. So I can take as an example here that u is y and v is x, for instance. Okay, and so if I want to draw again here in a similar fashion the flow, or just to very quickly sketch it to figure out what this is doing, well, I can just do the same thing and say that u has going to, the sine of u is going to be the sine of y. So I'm going to have a positive velocity in the x direction on the upper part of the domain and negative in the lower part of the domain. And the sine of the velocity in the vertical direction will be the sine of x. So I'm going to have upflow here, I'm going to have upflow here, and downflows on these parts of the domain. Okay? And so what I've drawn here is that the velocity in this quadrant is going to be going in this direction. The one in this quadrant is going to be in this direction. The one in this quadrant is going to be in this direction, and the one in this quadrant is going to be in this direction. In other words, what I've actually done is separating my domain along the diagonals and effectively having streamlines that look like this. Okay, so that's one, then I've got a second one here, I've got a third one here, and I've got a fourth one here, just for instance. And what this slope is nothing else than a rotation of this one by a quarter of quarter of pi. And therefore what I have is extension on this diagonal, right? The flow is being pulled away, the fluid is being pulled away from the origin on this diagonal. And on this diagonal I've got contraction, it's going towards the origin. Okay, so this is really what our strain rate tensor is doing, is contraction in this case again, and extension along the diagonals. Okay, so this is essentially what the strain rate tensor is. Now let's have a look at the vorticity tensor. So the vorticity tensor is responsible for solid body rotations within the flow. And to convince ourselves of this, we're just going to take an example. Once again, I'm going to take it in 2 dimensions to make the calculations relatively simple. So example, and there isn't many possibilities of 2-dimensional examples of this that we can do. So I'm going to just take my gradient of velocity to be, so the vorticity tensor has always a 0 diagonal, so there won't be any component on this diagonal, so that I'm not injecting any non-zero component within my strain rate tensor here. And furthermore, the vorticity tensor is antisymmetric, so I need to have this term to be equal to minus this one in order to have only a pure contribution of the vorticity tensor to my velocity gradient tensor. And so this is a form for the vorticity gradient, for the velocity gradient that will ensure that there is no component, no non-zero component of the strain rate tensor, but that there is, but that all this remains the components for, all this essentially fills up the vorticity tensor. So once I've got this, then I can just rewrite in a similar fashion as I did here. My problem for the velocity is du by dy equals 1, and I've got dv by dx, which is minus 1. And so, for instance, a particular solution to this problem would be that u equals y and that v equals minus x. Okay? And now if I try to draw in a similar fashion what the velocity profile looks like, what the flow looks like, and my xy plane, well, I can do it in the same fashion. So u has got the sign of y, so this is going to be in this direction. And in the bottom half of the domain, I'm going towards the left. But this time, v goes like the minus the sign of x. And therefore, this is going to be going downwards here. Okay. Minus the sign of x, so this is going downwards, and this is going to be going upwards, okay? And so if I write this down, what I have gotten here is that the flow on this quadrant is going in this direction, then the flow in this quadrant is going in this direction, in this quadrant it's going in this direction, and in this quadrant it's going to be going in this direction. And so what we have done here, we can obviously prove this in more details by calculating the stream function for this problem, but this is just a hand-wavy demonstration to have a feel for this vorticity tensor, is that we have created streamlines that are going to be circles centered around the origin and rotating in the clockwise direction. Okay, so that essentially comes from this velocity tensor, coming from the vorticity tensor, having exactly the same expression, and is responsible here for solid body rotation within our fluid. Okay, so in this video I've essentially explained how the velocity gradient writes, but I've also introduced a decomposition that is very useful in the context of fluid dynamics to understand what is happening to our flow and what components are going to be responsible for, in particular, solid body rotations and contractions and extensions. This concludes this video on the velocity gradient.